Good afternoon, guys. Welcome. Thanks for coming to this session. I hope you're rejuvenated after the lunch session and you're not going to fall asleep when we're going to be speaking about scaling our applications out. So let me introduce myself to you. My name is Bujok. I work as a software engineer for a company called Hazelcast. You can find me on Twitter under Tom Bujok or visit my blog under refisio.org. So before we go to the very core of the talk, let's first ask a question: why are we actually speaking about scaling our applications out? What's so new that happened in the recent, I don't know, months or years that suddenly everybody's speaking about scaling out? There's a lot of buzzwords. Most of the database implementations claim they can do scaling out. So the first reason is most probably the fact that, as you probably know, we live in the era of big data, the era of Twitter, Instagram, Facebook, and whoa, I touched nothing. What happened? Yeah, okay, that's the Moore's law. So we are living in the era of big data. We simply can process more data that we could process, let's say, I don't know, 5, 10, or 15 years ago. But we can't have a projector working. Maybe it's the cable. Maybe it's my fault. Yeah, no, it should be working, hopefully. So we can process more data. And the second fact is, most probably, we write applications that are slower. I don't know if you know the Moore's law that's claiming that's proving that the CPU speed is improving by a certain factor. There's also like a complementary laws claiming that we write software that's equally slower to the speed up than we get by the Moore's law, which means that there's actually no speed up in our applications at all. And adding the other factor that claims that we process more data. That's a perfect case for scaling your application. And what does it mean to scale your application out? Earlier, you could scale. Everybody was simply scaling, and it meant scaling up. It meant putting more CPUs, putting more memory, putting more stuff into your hardware, into your server room. You had a shelf of servers. You were putting some units into it, but still, it was working as a monolith. Everything worked over there. There were some solutions, like, for example, like Oracle RAC solution, where you had some two huge nodes or a couple of nodes synchronizing, but it wasn't really like that the system as a whole was operational, and you could process all the transactions independently on both nodes. There was always some synchronization going on, always some latency, always some waiting, always some stuff running in the background that, of course, you will have to have while you scale out too, but simply the characteristics of the solutions are different. Scaling out means having a lot of servers, not having 2, 3, 4 monoliths that are constantly synchronizing and keeping, let's say, all the data in sync on both nodes. It means that we can have hundreds or thousands of servers in different geographical locations, and let's say the first server has just 1/3 of the data, the second server has the second 1/3, and so on and so forth. And as a whole, everything works together so that your transactions can be processed, but the architecture looks differently. So we want to scale our applications out, and we also know that there's a couple of traditional RDBMS, like normal relational database products, and why can't we scale out with them? So there's a couple of so I won't say you can't do it because first question, and maybe somebody knows it, what database is used at Facebook to store the social graph? Who knows? Yeah, raise your hands. Who knows the answer? Yeah, over there? MySQL, exactly. So if I'm to claim that you can't do it, it's simply, it wouldn't be true. You can do it. You can do it, it will work fine, but the kind of core concept of relational databases is different. it has some characteristics that we see here. We have relations, we have the ACID model that's at the very core of the database. There are some transactions that are very slow while being distributed. So if I have 2 nodes, maybe it's going to be okay in one data center. But if I'm going to have a couple of nodes and they're going to be distributed geographically, will the transaction be quick? Of course not, because this node will be waiting for the other node to do some 2-phase commit or stuff like this. So you simply would have to tweak these solutions or not use some of these core concepts that are inbuilt in the RDBMS solutions in order to achieve what we want to achieve. Of course, you won't get sharding and partitioning out of the box. We're going to be covering these concepts later on. And backups, of course, you can get backups. It's not a thing that you can't do backupping, but it's always kind of the way the database supports it, right? So it's one specific way. We're having backups. It's mostly master or slave, and that's simply one way how you can do it in RDBMS. So that's the reason why we want to have a look at other solutions. And the reason I chose Hazelcast is simple. I work for them. I know the product. This is not like a advertisement of Hazelcast. I want to speak about scaling out. I want to show you some characteristics, what applications, so what you should do to scale out. And of course, I'm going to be showing it on the basis of Hazelcast because I simply know how to do it there and how to simply present it. But most of the solutions, modern, I don't know, NoSQL solutions or data grids or in-memory grids, they would be able to do this. So that's not advertisement, but there's just a short advertisement. Hazelcast is used everywhere. It's open source. It's freaking cool, and it's the quickest in-memory data grid and JCache implementation on the market. And when I say it, I may claim that's true because we take the benchmark of the competitors and beat them in their benchmark. So we are not tweaking our benchmarks and saying, in this case we are faster. We are beating them there. So that's enough about advertisements, and let's have a very, very simple scaling use case. Because in order to kind of present some concepts and present stuff that we're gonna be implementing, we're gonna be working on, we need to have some example, right? So what's the default use case with RDBMS? The default use case we are normally having is we are having some Bujok or whatever you call these objects right now. You most probably annotate them with some ugly Hibernate stuff. You have some data layer that's either implemented by you or generated or whatever it can do for you right now, the modern frameworks, and you store it in the RDBMS, right? RDBMS is normally like one instance of Oracle, MySQL, or I don't know, Microsoft SQL Server. You have a DB admin that gave you the access details to your database. You add it in your application, and you treat it as the single point of truth when it comes to fetching and storing data. Yep, that's the use case. As said, we could scale this out. We could try scaling this out, but we're gonna try to implement a different approach. And the first thing I'm gonna so there will be a couple of slides like this. It may be a slightly misleading. It's scaling out is simply the topic of the talk, and sharding is the concept we're going to be speaking about. So sharding is the first thing we're going to get out of the box in solutions that have the kind of scaling out capabilities inbuilt in them, like Hazelcast or other solutions. So sharding means that in our use case, in order to achieve sharding in Hazelcast, we're going to switch from the RDBMS to a Java util map. It's a Java util map. We know this map. It's an interface in Java, in core Java. Everybody's using it, and you would say, "Hey, why are we doing it? What's the point of it? Why do we actually?" RDBMS is like a cool concept. We can store it, and a map is in memory, right? So what are we achieving? So for now, we are achieving nothing. We are achieving simplicity because we are just using standard Java interfaces. We don't have to have any annotations. We don't have to do anything with our code to store our objects in the map. So we are simplifying. But what's cool about this map, it's a distributed map. So it's a distributed data structure. And in this way, we're going to we're going to achieve sharding. And sharding means that if you can see, there's 3 nodes here. And in RDBMS, it was like a monolith, and all squares, like red, blue, and green, that represent your data, were stored on one node. With sharding, each square, so each piece of data, or whatever it is, each partition is stored on a separate node, which means, as a whole, your data is on 3 nodes, and you achieve it out of the box, right? You don't have to say, hey, store 1/3 on this server and 1/3 on the other server. You don't have to do it by hand. It's out of the box partitioning. So how does it work? It works like this, that in step 1, of course, you can have one instance of Hazelcast, and all of the data will be in this distributed map on one node, right? But they will be stored in partitions. Partitions, by default, partition is like a container for data, we can say, and there's an algorithm that has characteristics of consistent hashing that's distributing the partitions to the nodes, like among the nodes. So whenever like a second node joins, one, of course, it's not going to be like this because we have like 3 partitions right now. In the step 2, it will be equally divided, but it's just for the use case, I'm showing it like this. So when the second node joins, some data will be migrated, and in this way, we are having part of the data on the second node. And then when the third node joins, the data are repartitioned again. Of course, it's done in a way that not all the data are being sent to all nodes. It's being done in a smart way. But sharding, remember the concept? It means that we split our data, and it's done automatically by default. By storing them, we don't have to, we don't have to take care of it. That's one thing that you don't have in RDBMS solution, and it's very, very helpful in scaling out, which we're going to see later on. So, what's cool about it? What's the second characteristic that we need? We probably need failover, right? So we are saying, hey, we're scaling out. We're going to have hundreds of nodes, and it's obvious that nodes go down. With RDBMS and with solutions like with the old style solutions or whatever you want to call them. The problem is that you always assume something, and you assume most of the time that the network connection to your database will be okay. If your network connection dies, or there's like a hiccup, or there's a timeout or something, your application is not able to process anything, right? You're waiting, you see some exceptions and stuff like this. So how does the failover work in the concept of scaling out? So with Hazelcast, it's done like this, that you have primary partitions and backup partitions. Primary partitions are simply primary data, right? These are the data that you are storing. Backup partitions are partitions that are reflecting your data just to have a backup, right? So you can see here that the data from the node 1, like the red square, is being backed up on node 3, right? So you see the red star, it represents the backup data, which means that, and so on and so forth. So every node has a configured number of backups. It may be just one backup. You may configure it like this, that you want to store 2 backups of each partition. So it's going to, let's say the red square would be stored on node 3 and node 2. You're going to have 2 backups. And what's the problem? So I didn't say one thing about Hazelcast. Hazelcast stores everything in memory, right? So that's the important issue that we have to take under consideration. And why do we actually need backups when we store everything in memory? And the second question, what happens if we configure a big number of backups? What happens with our memory? Who can answer this question? So what's the difference if I have 1 backup and I have 5 backups, if we store everything in memory? Yeah, you simply are using a lot of memory, you're basically wasting memory, right? Because you are storing backups. It means memory has a fixed size, right? So I can't stretch it. I can add some memory while I'm operating, while the program is operating. You have 8, I don't know, or 1 tera even now. But it's so if you fill it with your data, if you fill it with your backup data, then you can't use it for primary data, right? So you always have to engineer your application for the use case. And that means that you have to upfront say, we're going to recover if we have, let's say, if we have 30% node failures, right? So if 30% of the nodes go down, our backup count is enough to cover for this case, right? In our case, we could recover when one node goes down, right? Because we would have a backup. Even node 1 goes down, we're going to recover from node 3, and the blue star will be backed up somewhere else. But if we lose node 1 and node 2, then we are screwed. We lost some data, right? We would have only 2/3 of the data because we would have green data and red data, but blue data will be lost. So that's how it works. And of course, failover means that if one node goes down, what I was explaining right now, you can see that the box is moved in a way to recover, right? So your cluster is operational. It happened out of the box. You didn't have to do anything. Hazelcast detected, or the solution detected that, oh, one node went down. There might have been some kind of some slot where you couldn't process your transactions because it's a system that has to, it has some default timeouts, right? The node might have some, internet connection problems, or the network might have been congested. So it will wait a bit to see, oh, is the node really down or not? But when it detects it, you didn't have to do anything, and this is also not inbuilt in standard RDBMS solutions. So that's another characteristic that's pretty important. And of course, when we say we need to scale out, we also want to scale out geographically. And that's possible with most of the solutions. They're normally connect via TCP/IP, like Hazelcast in this case, and yeah, you can split your clusters in a way you want to do it. There's also like a multicast discovery if you are in one data center or your private data center. There's also like AWS or some cloud plugins to connect your nodes in Amazon Cloud and stuff like this. What's really cool about Hazelcast is that's a short advertisement because not that many solutions are implemented in Java when it comes to NoSQL and stuff like this. It's implemented in Java, so you can operate in an embedded mode. Embedded mode means that it's just a jar, you add it to a class path, you start it, and it works, right? You don't have to have any provisioning, you don't have to do any Dockerizing or puppetizing or stuff like this. You just start it as a normal library, and it works. Of course, you can do it within a client-server mode, depending on your use case. So that's what's also important, and that's also not that obvious with standard RDBMS solutions to have like a geographical spread in a custom way or way you want to do it. So what's also really cool, and that's then I'll ask you if it's possible to do something like this in RDBMS solutions, so you can think about it right now. I'm speaking about it. So with most of the solutions like Hazelcast, you can do some kind of function processing, and here we can have a look at this very, very complex data processing theory. You can smile you can laugh that it's simple, but it's like a thing that's killing most of the Java applications, right? We do not really think about it, because how do our applications work? Let's imagine a case, you have this employee Pojo, you have your data access objects layer, and you have your database, right? So you are taking your object, you are serializing it, Hibernate is doing some magic mapping, is generating some SQL, you are sending this function to the database. Database is fetching some data, sending it back to you. You are deserializing it, demapping it. You are creating some objects, of course, generating a lot of garbage on the heap because you're going to dispose this object soon. And then what do? You increment the flag, or you do some business processing like with your object, and then you do Hibernate save. And it's taking the object again, it's serializing it, mapping it, creating some update function or whatever, and then it's sending it back to the database. So you can see there's a lot of back and forth. If you are doing it like I'm described right now, but that's the most common use case. And is there a different way to do it with RDBMS? I can already say this is a way that Java developers don't like, and it's discouraged by many people to do it. So what would be a more optimized way in a standard way, right? How could I improve this processing flow? The answer was stored procedures. Of course, stored procedures can do it for you, right? You just write some kind of statement, you send it, and it's going to be executed on the node. And in my opinion, they are awesome. For certain cases, of course, you cannot generalize, but they are really good. But it's discouraged because, like, your architect will tell you, hey, how will you unit test your stored procedure? And you're going to say, I can't. So it's like, no, I can't do it. So yeah. That's the thing. With Hazelcast, you can do it. There's something called like entry processor. There are very similar concepts in other solutions. So it works like this: that I'm sending Java code, so I can unit test it. Right? It's simple. It's just a normal Bujok that extends another class, and yeah, and what it does, it's like I'm not fetching the data in order to process them. I send the function to the node, and the function will be executed on all the nodes, on all the partitions, right? So, which means that the processing will be local to the data, right? I'm not sending any data. Look at how much better it is. We are not doing any serialization. We are not generating garbage. We are simply sending like a very, very tiny function that will process all the data locally on each partition. And what's also cool in this case, because we're just saying, hey, we have backups, right? So if I do entry processing like this, and I change each piece of data I have in my map, in my partitions, what should I do with the backups? What will happen to the backups if I change every row on the primary partitions? What do I have to do with them? Can I keep them as they are, or do I have to do something with them? Sorry? Yeah, synchronize, so I have to update them, right? I have to update them. I have to exactly get the data back in sync so that the backup values are the same as the primary values, right? But look, the backup values are on different nodes, right? So what would happen in a dummy solution if I just implemented the entry processor in a way that, I'm processing the primary partitions and then the backup synchronize? Would it be optimized? Would it be okay? What would be the problem? Exactly. It will send all the data. It will synchronize row by row. It will take the data and send it to the other node. So, which means we are not at the safe side again. We are laughing from the hibernate approach, but we are doing something in a probably more stupid way. So no, you don't do it. You don't have to do it like this. What you've got is like a backup entry backup processor. Which means that's so cool, you can execute your logic on your primary partitions and on your backup partitions, meaning that all the processing that you are doing is local to the data. And entry processor is running on a partition thread, which means there won't be any modifications in between, so your data will be perfectly fine. So that's really cool. That's a very, very, very old concept, as said, like stored procedures, but it's a game changer, right? It's a game changer because if you have to process a lot, if you have to change a lot, right? You are not fetching the data to modify them. Yep. Question? So the question is like, what happens when the entry processing is, so queries are not running on the partition threads. Hazelcast has kind of like this duality. So all the data modifications are running on a partition thread. That's only one thread per partition, which is like, you can say like an actor for a partition. But but the queries are running, there may be more threads and the data structures are concurrent. So I can modify and query, right? That's the if you have to have consistency across that, you would have to do some locking that I'm going to be showing later on. Okay, that's the question. That was the question. Now we move to data affinity. So that's also a very, very cool concept that you can meet while having a look at the NoSQL stuff. Data affinity. This is very important because what we are trying to do, we are trying to distribute the data, and we are trying not to pull the data across the wire if it's not necessary. But there's also another use case. Imagine that you've got your map, and you've got yeah, a lot of data there, right? So you've got your persons or employees, but you also have got some in the RDBMS, you would have a table for personal data, you would have a table for salaries and probably like a foreign key, or you would have a table for addresses and one-to-many relationship or stuff like this. So yeah, and what would happen if I had an employee and I was processing the employee locally on each node, but let's say the employee itself was stored on node 1, but the data were distributed in a way, because the distribution happens automatically, right? So we can control it to some extent that I'm going to show right now, but it's done automatically, right? So it may be the case that that all the other data about James Bond, which is the first employee, are on a second node, right? And I'm doing something with James Bond, I need his address, and then I'm going to do a get address or something, and it's going to be a remote call over the wire. And of course, that's a huge problem if you're fighting with latency and high throughput. You want to do everything locally as possible. Then you can use this data affinity, which means that all the data that belongs together will be stored together, right? Will be stored on the same instance or in the same partition. So that means that I can do all my processing or looking up or stuff like this locally in one Java method, even though the data are distributed. But for each object, it's going to be local. And this is done in a very, very simple way. For a salary, you can have a partition key. That's the key of the employee. And that will guarantee that the hashing algorithm will treat all the keys in the same way, because it's the same value, right? So it's going to be the same partition. So that's very simple trick. What's also cool is that because Hazelcast in this case, it's not only like a it doesn't only have the features of like a NoSQL solution or like a data store, in-memory data store. It implements Java util concurrent structures, and one of them is like an executor service, but it's a distributed executor service. So it's an abstraction over executor service, and it works like this: that if I have a runnable or like a task or something with normal Java executor service, you submit it, and it's going to be processed on your JVM, right? With this one, you can submit it, and it can be it can be executed on any of your nodes, right? So it enables distribution out of the box without any additional logic. But you can also say, hey, for this task, I'm just updating one employee, and I'm updating the salary of one employee in the call, and I want it to be executed on the specific node according to this partitioning key, right? Because if I did it differently, it would be, let's say, James Bond would be the employee that I'm modifying would be on node A, but the executor service might have executed it on node B. And this would be, again, a remote call to fetch the data that we want to update, and we don't want to do it. So these are things that you normally do not really think about while you work with RDBMS solutions. A, you don't have these features; you will have to do it all by yourself. And B, like in general, people are not sensitive to these things, right? We are just coding our stuff in Java. We have a couple of annotations. We are modifying something, invoking save or persist or update or merge, and for us it's magic. It's persisted, right? But what's really happening there? How many remote calls do we have there? How much serialization are we having there, and stuff like this? These are things that are really important when we scale, because we scale mostly because we need to have more throughput. We need to be able to process more. So we cannot have logic that's slow, or we cannot have unoptimized things, right? First we optimize stuff, and then we scale out, right? So, yep. So then you'll say, okay, but how do I do it? Because all my data are stored of a couple of nodes, right? So I want to query it. I want to get some results. Like with SQL, it's easy. I'm just doing select something from something, and boom, I get the result, right? Here, how do we do it with a map first? Because it's just a map. So do we have to iterate over all elements to get the data? No, it's not like this. There's a query language. It's like there's two solutions actually with Hazelcast. One are the predicates, so you can build it's like criteria API. You build some queries using API calls. You can unit test it, and you know it's it's going to work. And the second one, if you still prefer to do stuff like this, like in SQL, you can use an SQL predicate, and you can type your query in it. Of course, yeah, this you can make some mistakes that will be validated during runtime. It's not like a ICO SQL or something. It's a distributed SQL called in Hazelcast. It's limited, right? So it doesn't have all the features that a normal SQL language has, but it's even impossible to have all the features because it's simply a different solution, right? So you can do it, but you can do something like this. And what's also cool, and what probably you wouldn't expect, is you can index data. So you can index data in a map. That's very cool. Why do we index data? We index data in order to have a constant lookup for our queries, like to have a constant time response for our queries. Let's say I want to get all employees that are 30 years old, right? When I build an index for it, I'm just going to look it up in the index, which is very, very, very fast. If I don't have the index, you have to do a full table scan. That's what the normal RDBMS do, and here you have to do it too. You have to go through all the data, and you have to check and compare what's the age of the person, of the employee, and what's the age that I want to fetch. And it's obviously going to take time. Yeah, and there are like 2 indexes, sorted and ordered and unordered. The advantage is that with ordered indexes, you can have range scans, like you can use index for range scans. So I want all employees that are between 25 and 28 years old. But obviously, you need some more processing to sort the data in the index while being modified, which is a bit more heavyweight while we execute our store operations, right? So we still think about it, right? It's not like this that I just enable index and boom, it's working. I think about, do I need sorted or unsorted? What's the advantage? What's the disadvantage? What's the cost? Everything happens at a cost, right? So indexing happens at a cost. Maybe I don't need indexing at all. It's gonna require some processing to have the index, and B, it's gonna use memory, right? It's gonna use memory because the index is in memory. So yeah. So these are the things we are trying to think while we work on our applications, right? And we want to scale out. So another feature that's kind of on a side note that's really cool in these solutions, because you can use it in a different way, right? It may be a cache, it may be your data store, it may be just some store for hot data or for some processing you want to do. And sometimes the question is, yeah, but we've got this RDBMS. You are showing us cool stuff, so we want to use it. It's gonna work out nicely for us. But we at the end of the day need to store the results in the RDBMS because we have some business. I don't know what's the most common enterprise software use case. They have some reporting, and reporting is like a BI stuff in a different department. Then they generate the reports using the crazy tool, and we need to reflect our data. We have to reflect our updates we are doing in the data in the RDBMS. So you can use this map loader, map persistence basically, map store and map loader. In both directions you can implement it. There are different ways that I'm not gonna be covering right now, but it's pretty much the thing to reflect your data modifications to the data store. Yep, so consistency. That's if you are used to transactions and if you are used to having everything consistent, everything well structured, and then doing all your modifications in a transaction, I have to disappoint you. In NoSQL, that's not I have to disappoint you halfway, because you won't have such transactions, of course, because as I said, distributed transactions would be slow. How would you imagine it worked if you had like nodes in different countries and you were opening a transaction and doing some modifications? So it won't work. You don't have it, but you simply kind of engineer your data in a different way, right? In the relational database, you want a normalized form. You normalize your data. You have tables. Then you update. So when you update employee and his salary, you update 2 or 3 tables, right? It's optimized to work in this way, and that's the reason you need a transaction, because you are simply updating 2 entities. With NoSQL, simply people are encouraged to think differently about the data. You think in aggregates, right? So if I have my employee, maybe I need his salary in the employee object, right? So I can, in most of the solutions, in all I can say, you can update the aggregate safely, right? Because there's only one operation. Aggregate is just one entity, and you are updating it safely because it's just one operation on one piece of data, right? What's the problem with that? The problem with that, or a different approach you need to kind of implement, is that you will have data duplication in many cases, because but it's like what's really encouraged, like even Cassandra, when they tune their database cases for like to the very limit, they say, hey, you have some data here, you have some other data here, it's the copy of this data, but for this query, if you want to have this throughput with this latency, you have to have the data duplicated. Yeah, and you have to work out your use case, because it also depends, right? Maybe I'm doing 10 million queries and 10,000 updates. So I engineer my data structures for my use case. I want to be able to read very quickly, and when I update, maybe I'll have this time span when I synchronize this duplicated data. And yeah, it's going to be slower, but the read query performance will be very high. So with here you can do pessimistic locking. That's something that you can do on one aggregate, so on one data entity. You simply do a lock, then you can do whatever you want to do with it, and then you unlock it. But that's obviously slower, because while you lock it, you can't do anything else with the data, and so nobody else can update this value. There's something similar that you have, like that we have in Hibernate, or basically in a relational database, where we do update if, right? So if the data is equal to this, I want to update. Otherwise, it means somebody has already updated it, right? So we are not allowed to update it, because we will override some new value. Yep. So that's the concurrency control. If you want some more performance, you will say, hey, it's still not enough for me. I still want to have more and more and more. You can enable something that's called near cache, and different solutions have it on they have it on different levels, right? So Hazelcast, you can call it a cache. It's distributed cache. It implements JCache implementation. But you can have cache within cache. So you can have near cache on the client, and it means that whenever I'm calling something, I can store. Without near cache, whenever I call something, I want to get a value from the node. I'm just connecting to the node, right? I'm using a client to connect to the node, and if it's not in the same JVM, it's a TCP connection, so I'm invoking a remote operation, right? If I'm asking always or frequently for the same value, so let's say right now probably everybody's checking the results of the games of Euro 2016, right? So, and most probably in Germany everybody's checking the how Germany played, and in Poland how Poland played. So it's easy sometimes to predict what kind of, and the results do not after the game finishes, they do not change, right? So I can basically maybe cache them so that I don't have to hit the cluster every time somebody on your website is asking for the details of the result, like who scored goals or stuff like this. So yeah, so that's how it happens with near cache. You basically have it on the client. What's the disadvantage of this? Who can tell me what can go wrong, or what it means for the client right now? So what? On the read operation? Yeah, no, in general, yeah. Sorry? Obsolete data, exactly. So obsolete data, if the result of the game changes somehow, because UEFA decided that it changed, then you would have to invalidate the data, right? So the client has to get invalidations, which is a remote operation from the server to the client, right? So if you suddenly have to invalidate all your data in your near cache, you're gonna have a lot of calls. So it's optimized if it's all data, but if you have to selectively invalidate some data, then it's gonna be a lot of calls. So That's the problem. And the other problem is the client will also have some memory, higher memory footprint because the data will be stored in memory on the client. So what's also cool when it comes to reading from having some more performance is the read backup data. So in Hazelcast, currently it's not possible to read from backup from the client. So in this case, if we come back to this case just to see the nodes, it would be possible, even though, let's say, the primary data, the red square is on node 1, but the backup is stored on node 3, you can enable reading from backup from the client and read from node 3, because maybe node 3 is my data center and node 1 is in a different country, right? So in many solutions, you can read the backup data. Of course, it's eventually consistent in most of the solutions because, yeah, you can get some obsolete data. It takes time. With Hazelcast, it's not possible from the client, but it's possible from within the node. So if, let's say, I'm doing some entry processing, or entry processing is a bad example, but if I'm doing some executor service submission and I'm fetching some data on node number 3, and the data reside on node 1, then it would be a remote call from the executor service, right? But I may enable reading from backup and fetch the data from node 3 locally, having some, of course, chance that it's going to be eventually consistent, but yeah, that's how it works. So that's also pretty cool. Yeah, and there's some other cool stuff you can do. I don't want to go into the details. What I want to tell at the end, I mentioned it already, that it also implements Hazelcast. In this example, implements JCache implementation. So if you are using some web session replication or second level cache for Hibernate or stuff like this, you can use it. I tried to show you like the main things you have to think about while scaling out, the main problems you may face, or the main issues, the main design kind of, milestones, right? A case is never equal to another case. You always have to think about your data. You always have to analyze, how do I store them? How do I, maybe I duplicate, maybe I denormalize. It's never like this, that one specific data storage is perfect and it's going to be very quick for reading and writing, updating and caching and whatever. It's always very, very specific. And if you want to achieve high scale and very, very high throughput and low latency, you always have to think in this way, right? You think, this is my use case, I want to achieve this. What do I do with my data in order to achieve it? In our presentation, we've just seen the features of the map. It gives you most of the features that standard NoSQL solutions have in Hazelcast. It implements a lot. You have all of the Java concurrency API implemented in a distributed way. You also have most of the collection stuff. Also other features like, let's say, ring buffer. If you read the disruptor pattern or disruptor approach with the ring buffer, our ring buffer is actually was implemented on the basis of that, and also with some Martin Thompson's feedback. So it's pretty much cool. There's also there's a lot of stuff there. So I encourage you to have a look and see for yourself if something will work out for you. Thank you very much. We still have, I think, 2-3 minutes for questions. If somebody wants to ask a question, you can do it right now or just approach me since people are leaving. Mm-hmm.
When Hazelcast is using bit, this is still distributed among several nodes?
What?
When using as a jar in the bit?
Aha, we are using, it's a jar. So Hazelcast is a jar.
Yeah, so it will distribute the memory among several nodes, even though it's embedded in a jar, or to be distributed as we use in a client server.
I'm not quite sure if I perfectly understand the question, but maybe if you come forward, then we can discuss this case. Any other questions? So your question is about the jar?
Yeah.
It's a jar, yeah?
Yeah. You showed it could be used in client server or as embedded
Yes, exactly.
Yeah, and I'm wondering if when you use it as embedded,
Yep.
you will still able to communicate with several nodes, so your data
Yeah,
will be
yeah.
available
Yes.
in other nodes.
Yeah, so even in the embedded mode, you can connect to another nodes. Yeah, you have to have the jar, right? So either you have to have the client jar or the core server jar, right?
Okay.
And then if you have it on the class path, it works, yeah.
Okay. Okay, but the Hazelcast is in the memory entire, and but did you manage? Can you manage, to load entire data in memory, because often the amount of data is so huge.
Yeah.
So do you only read the partially, and then?
Yeah, it's like then you need, so you need more nodes because each node has, let's say, 10 gigabytes of RAM, right? If you want to store 100 gigabytes of data without backups, you need 10 nodes, right? If you want to store 1 tera, then you have to see how much RAM you have, how many backups you want to store, and then you've divided, you're doing the maths, and you see, how for your specific use case.
So
Yeah.
all the time you are trying to load in the entire.
Yeah, everything's
collection.
always
Everything,
in memory. Yeah,
everything is in the memory.
there's no data storage, no nothing like this. No.
Okay.
Like the data storage to a file or to a database. Yeah.